Thank you so much. Yep. Last talk of the day. We'll talk about machine learning for very, very small systems, especially compared to what's all the rage today with giant language models, generative AI, and so on. This will be completely on the different side of the spectrum, talking about how we can do machine learning that is useful for different kind of tasks at the milliwatt size on small microsystems. So my name is Jon, I'm from Sound Sensing. We monitor ventilation systems, such as the ones shown here, and our customers operate buildings such as this. And for us, we use machine learning to automatically analyze to detect anomalies. And today, we'll talk about why machine learning on microcontrollers is relevant. Like, how can we do useful things on such small systems? This niche is called TinyML. Or Edge AI is also getting popular as a term. We'll talk about the emlearn project, open source project that I maintain, some projects that has been made, real-world projects with emlearn, and we'll cover a quick how-through too. So, machine learning on microcontrollers and embedded devices. What is it used for? It's primarily used for sensor data analysis. So we have some sort of sensor node. We have the sensor itself, it can be camera, accelerometer, microphone, radar, and many LiDAR, etc. And we want to process that information or all that data and extract the useful information from that large amount of data. And only, like, for example, directly act on this in robotics, for example, or we might transfer it over to a larger system or potentially to a cloud. But just the relevant information, not all the useless data. So this allows some key benefits. We can make standalone systems that operate with low latency, guaranteed latency. We can make highly power-efficient systems where the sensors can run for multiple years on a single battery. And we can also make privacy-compatible systems because we don't transfer all the potentially sensitive data. And we can also make things low cost, which is relevant because it enables massive scale in terms of the number of units we will deploy. And this is already used in many areas, for example, in consumer technology, keyword spotting, so detecting Hey Google or Hey Siri, and so on. That's using a microcontroller, then wakes up the rest of the system. Or if you have a sleep quality tracker or a fitness tracker, that will also use this kind of technology. In industrial case, for example, you can use this to track the health of animals. We use it to track the health of machines. Or you can just use it for fun projects at home. For example, you could make a smart doorbell, which opens the door for your cat, but only if it's your specific cat and not any cat. Or you could make a magic wand, which you can use to make a gesture to control some of the devices in your home. And these microcontrollers, they are essentially a full computer, but a very, very small one. You have, for example, maybe 1 kilobyte of RAM, or maybe the largest system has 1,000 kilobytes of RAM, and similar in terms of the program space. So all the machine learning, all the code needs to fit in there. And we're mostly doing inference on the edge, not so much learning on the edge. The price point might be as low as 10 cents, US cents, or as much as $10 for a microcontroller. And this is a huge area. Like any electronics will have one or more. Like your car will have almost 100 microcontrollers these days. So there are over 20 billion devices shipped each year. So this is tiny chips, but massive scale. And this is increasingly available for hobbyists. So you can program these kind of things with the Arduino IDE, for example, or with MicroPython. But efficiency is key. So the emlearn project, I started in 2018 as part of my master in data science. Before I have a background as an electronics engineer, I wanted to combine those skills. And there's two aspects to these kind of systems. You have the training process. That's quite standard. It happens on your computer. You use familiar tools such as scikit-learn or Keras. And you have a pipeline that spits out the deploy model. And then we have the emlearn project. It's a Python library that you install, and you have a one-line export to an efficient device model. And then on the device side, you can then deploy this either with emlearn C library, which is written in portable C99. It will run on any system that can run C, which is basically any embedded system. This is the lingua franca of that area. And it's even used inside the Linux kernel modules, for example. Or you can use it with emlearn MicroPython, which is, I think, quite interesting because most people that do machine learning, they know Python primarily. So this enables to do all the application logic for even this kind of TinyML type systems in Python. And then the emlearn library is implemented in C and exposing Python APIs. emlearn supports the most common tasks, such as classification, regression, and anomaly detection that are relevant for this kind of sensor data embedded use cases. Support a range of simple and effective embedded friendly models. So this is a subset. So there's no large language models. There is nothing like that. But you have, for example, decision trees, random forest classification, k-nearest neighbors. Then you can do simple on-device learning or adaptation. Also some small neural networks, multi-layer perceptrons, convolutional neural networks. And here are some projects using emlearn, of course, being open source. Most of the projects out there we will never hear about, but it's at least referenced in over 40 publications by scientists across the world. And here's a selection of examples to keep it kind of real for what is it used for. So from Virginia Tech, they created a system to track the health of cattle. So you use an accelerometer that is mounted on the cow, and in that system, you automatically analyze with a decision tree model the accelerometer data and determine if the cow is lying, walking, standing, grazing, or ruminating. These are like the stages of food processing for the cow. And then you transmit this data over LoRaWAN, so just not the raw data, but the activities, so like the classes, what is this cow up to. And then this is used then to track, to check for abnormal behavior. So like if the cows are not eating for a long time, that's concerning. That's something you might want to check out. And doing this all on the sensor enables it to run under 1 milliwatt, which is 50 times lower power consumption than sending the raw data, which is really important in this kind of case because basically it allows you to have 50 times the battery life. Here's a project from Samsung Research where they estimate the breathing rate of the person wearing this kind of earable or device, and they use a combination of audio data as well as the accelerometer data to determine how quickly you're breathing, which is very important to track for those that have respiratory health problems. And this is a practical solution that can be used and worn every day, not just in a clinical context. And again, this is important that the power consumption is not too high so that you can still use this for like a couple of days without having to worry about battery life. Here's a more like fun project of mine using an accelerometer and a timer that can be attached to a toothbrush, and you automatically track how long you're actively brushing your teeth. Because you are supposed to brush your teeth for at least 2 minutes every time, and most of us don't do it. So this device can help you. So this is something I did over Christmas, just for fun. And one thing I'd like to highlight here is that I collected and labeled the data for this in just a couple of hours. So these kind of projects are possible also with a low amount of data, because the problem is not so complex, like determine like a realistic type of shaking that you do when you brush your teeth. That can be done by just collecting like 5 sessions of training data with 2 minutes each time. So, and that makes it really fun to get into. Like, you don't need this massive data set, so you can go directly and solve things that you're interested in around your house or home or business or whatever. So there's full example code on that available online. Here's like more of a research project of mine, like trying to really find out like how cheap can we make these systems, like it's still a useful system. And I posed the question, can we make a useful TinyML system for under $1 in total component costs? And the preliminary answer is yes. You can do either motion analysis, so use an accelerometer, and you need a battery and the BLE transmission, all that, for under $1. So it's like the BOM is around 70 cents for that. And the models need to fit then in the microcontroller we have for that, which has 8 kilobits of RAM and 64 kilobits of flash. And that's actually quite a lot from my perspective. So I think we should also be able to do audio analysis with that, with small neural networks. So that is also possible. So you can't do both. You can't have you don't have enough money for both sensors, but you can do either. So emlearn has this C library. So that's the easiest way to deploy on the vast majority of devices because C is the most common. And you train the process using the standard Python ML libraries. So, for example, Keras or scikit-learn. And yeah, we support a selection of different models there. Then you use the emlearn library with this convert function to convert it into an efficient model. We do a couple of simple optimizations there. And then you can use the save function to generate some C code in this case. So this is just some example code or like sample output for a neural network. And it will look quite similar for the other kinds of models. You can then include the generated header file, and you construct your input data that you would typically read from your sensor, and it might also include some feature engineering or pre-processing there, and then you pass the data to the predict function that we provide, and that's all you need in order to run machine learning models on these kind of devices. The alternative is to the emlearn C library is to use the emlearn MicroPython library, because as I mentioned, many that do machine learning, they speak primarily Python, and it's very interesting to be able to use those skills directly on these kind of devices. So MicroPython implements a subset of Python 3, so it's a really nice practical way of getting into these kind of microcontroller devices. And they have a really nice feature, which is that you can load C modules at runtime. So similar as on a real computer, you can just like do mip install in a MPI native module, and then you can drop in efficient C modules that you can use from Python. And that's quite unique in this embedded space and very useful. So we provide then a range of modules. They're standalone, so you can install just what you need. For example, infinite impulse response filters for doing digital filtering, very common to do random forest or tree-based ensemble models. They are very power efficient, and small, so they're very useful, and also fast Fourier transport. So we saw that it's useful to also provide some DSP functionality because it was a bit lacking in the MicroPython space. And you can do convolutional neural networks, so there's examples doing image classification, etc., available in the repository. And doing this is at least 5 to 20 times faster than, for example, generating Python code and executing that with MicroPython. So you get the convenience of using Python, but you get the speed benefits and the size benefits of these C modules. And the process of using that is very similar. You train your model, use the convert function. In this case, we often save the model as a file, because MicroPython has a file system, so we can copy the model definition over as a loadable file. And then, one installs the library with just one line as well. You can create the model, you have to specify the capacity, and then we load these, the model definition from the file system. And then, again, you read your sensor data, and you pass the data to the model predict function, and you get the classification or regression or anomaly detection output. So that's all that we had. So in summary, machine learning is used in embedded systems to automatically analyze sensor data. That's the predominant use case. And then we can make practical applications in this space with just a few kilobytes of RAM and within just a few milliwatts of power, or just a few dollars in terms of bill of materials or hardware costs. And emlearn is an open source project to help deploy machine learning models to microcontrollers, and you can use it either with a C library or MicroPython library. So there's some resources, and you'll find the slides, of course, online with more information, including some other talks that go a little bit more into depth in particular aspects of this niche and the library. So thank you so much.
Thank you very much. This toothbrush was this toothbrush. I have to buy it. Like, do you sell it? Do you sell it?
No, it's open source, so you just download the 3D printed files. If you have a 3D printer yourself, you use it there. If not, you send it to someone to print, and you download the code.
Okay, that's cool. Any questions? Yes, please, and shout it.
I was wondering, how common is it that these small devices have some kind of a co-processor, like a vector processor, and could you exploit it on this low level?
Okay, yeah. So the question, I'll repeat it. So, are there devices that have some coprocessors that you can use, like vector processing and stuff like that? Is it common or not?
Yep, it's getting more common because this is doing machine learning is more and more common and relevant. But hardware takes time, right? So it's not like 99 will have it. But there are some recent instructions. So ARM has like standardized SIMD instructions for the Cortex M4 that is quite useful. Can give you like a 4x benefit on like neural network type problems. And then there's Helium that is coming. They have standardized it like 4 years ago, but the devices are not really out there. But then there are, on the ESP32, there's the S3, which has a bunch of smaller vector instructions. So it's possible, it's getting possible to do like get like a 4 to 10x type speedups. And then there are now, like ST just announced a new microcontroller just before Christmas that has like a dedicated NPU, they call it, neural processing unit. So definitely this is becoming more and more common. And on the high end, like if you do like powerful image classification or object detection, for example, you want to use that. But then if you're doing with accelerometer data, for example, it's usually overkill. And sometimes it can be less power efficient because you have this coprocessor, you need to shift data in and out. So it's definitely getting there, but you can do quite a lot without them right now. So it's good.
Will emlearn relate to those?
We'll see how much we implement like those instructions. The ones that get common, yes. But right now we prefer just doing plain C, runs everywhere, simple, and usually enough.
So one question from mine. Do you see any time when those microcontrollers will be running LLM inference?
LLM? Oh, yes. There's a surprising amount of buzz about LLMs and this all kind of... I don't quite understand the use cases yet, but it might be relevant for robotics. But there's at least a lot of hype around it. We will see in a few years if there's like useful things or not. I don't really know. But yeah, definitely a lot of hype.
Like a toothbrush talking to you.
I'd like the toothbrush talking to you. Like tell you need to do more, like a personal trainer. I don't know.
Okay. Thank you again.
Thank you so much.
And that was the last talk. And let me pass the mic to